This is our Reticle Particle Inspection System 2022 Senior Design Project. This machine will accept customer reticles for inspection before being used in lithography systems. The components of this machine include a 1 degree of freedom mechatronic system, a dark field camera and enclosure, an inspection light source, and a human-machine interface. The mechatronic system is powered by Arduino and a NEMA 34 stepper motor. Get an image of that. The camera is a Genoptic macro dark field imaging camera utilizing Matrix IntelliCam software to capture the image of the reticle. It operates on the principle of dark field spectrometry, where dust particles on the surface of the reticle reflect into the camera and all other light dissipates. To operate the machine, a customer loads the reticle onto the machine trolley. Once loaded, the customer activates the machine through the human-machine interface. The trolley will then travel into the enclosure. Once inside the enclosure, the inspection light turns on, and the camera takes an image of the dirty surface. The image is displayed on the machine screen. The specs seen here indicate dust particles on the surface of the reticle. Because the machine is not operated in a clean room environment, a dirty reticle service is expected. At this point, the customer can retrieve the reticle from the machine and take it for cleaning as necessary.
Hello, my name is Angelica McAfee and I'm a computer science major.
I'm Min Huang, I'm a mechanical engineering major.
I'm David Hanrahan, I'm electrical engineering.
I'm Ari Columbus, and I'm a mechanical engineering major.
I'm Tim Cusack, and I'm a mechanical engineering major.
I'm Jack Baker, and I'm a computer science major.
I'm David London, I'm a mechanical engineering major.
We are designing a standalone reticle inspection system to detect particle contamination on the surface of reticles used in lithography systems.
Thank you.
Hello, we are the Reticle Standalone Particle Inspection Senior Design Project, and we're going to take you through our outline, which is going to include our problem statement, motivation, approach, and demo. Okay, so our problem statement is that in EUV lithography, the machines use semiconductor manufacturing proprietary photomask template. And the issue with this is that the reticles are highly susceptible to contamination. So the result of this is defects which impact companies' production and cost yearly.
The motivation. So the significance of semiconductor lithography systems within the chip making industry is seen in benefiting technological advances within our era. For instance, life-saving devices and equipment that involve powerful systems rely on our product to deliver the highest quality microchip to date. The reticle particle inspection system will yield benefits to all engineering disciplines in the use of designing or building modern technical solutions, as well as supporting the expanding supply chain.
In industry, lithography machines are the final test in determining the acceptance or rejection of the reticle. Our product will apply the complete inspection of the reticle backside surface. Our research steers toward helping companies like ASML adopt cutting-edge alternatives through revolutionary change in industry. Our product will deliver more jobs, business opportunities, and production to our technologically driven society.
Our approach to designing this system was to make a secondhand particle inspection chamber around an existing camera system. The challenge in doing so is to build a system that's capable of delivering a high resolution reticle inspection within its enclosure. The challenge is in capturing this image on the surface of the reticle using the dark field imaging and identifying these particles to help the industry.
By creating an enclosure holding given inspection chamber, camera, and computer, we can properly simulate a light-free environment. The computer will run the mechatronic system in an easy-to-use GUI interface. A 1-degree mechatronic system will be used for reticle placement underneath the camera. This frame around the camera and given inspection chamber will be reinforced with 80/20 beams.
The reticle will be placed on a tray moving in and out of the darkened inspection chamber. A twin rail system is located inside the system to hold the trolley linear during the movement. Then there's a servo motor placed beneath the chamber attached to a ball screw system that's also attached to a bracket. And the servo motor moving the trolley along the rails is controlled by the Arduino microcontroller.
So our demo so far is the system includes a stepper motor with an encoder that is run by an Arduino. One goal was to provide data for this project to be improved upon further. As we can see here with my mouse, this chamber was actually already created before we had started our project, and this is what it looks like currently. So with our enclosure as well as our lighting systems, we were able to get this photo as well as the GUI has been created. So we're still in the process of completing our entire project, but for right now, we have actually successfully gotten a picture of our reticle. Thank you.
Hi, we're the Robotic Surgery Training Dome group. My name is Jenna Madigan and I'm a biomedical engineer.
My name is Stephanie Prado.
My name is Claire Sorrotanto.
And my name is Chloe Stokinger, and we aim to improve robotic surgery training by providing quantitative feedback.
So this is the beginning of the slideshow for the Robotic Surgery Training Dome Senior Design Project.
Our Robotic Surgery Training Dome aims to improve quantitative feedback given back to the users while practicing suturing, given the sensors and Arduino incorporated in our design, and this should improve the proper technique of suturing for surgeons. The motivation for this project was basically to improve the training aspect of surgeons to lead to less harmful invasive procedures on patients and improve healthcare overall. Our design gives proper feedback, unlike other designs of robotic surgery training domes on the market today.
Our dome design is made up of two parts. The top piece features legs that are 30-degree outwards with slits for the conductive cord. The conductive cord would measure the pulling and the tugging forces when suturing. The bottom part of design is an upside-down bowl with silicone pieces and the pressure sensors. These pressure sensors would measure the force of pressure when suturing. For the software component to it, it features the Arduino connections and MATLAB code implementation. So the sensors would be connected to Arduino boards while the code is written using MATLAB for enhanced graph display. Literature surveys that we conducted gave us a threshold value for when a surgeon would apply too much pressure. This threshold value was implemented in the code to give green and red light feedback.
For the final demo and validation points of this project, we were able to calibrate the 5 sensors that we have on our dome with known weights. And by using those known weights, we were able to convert the initial voltage read by the Arduino and convert that into force, which you can see on this graph right over here. So as we added more force, the voltage went up, which is expected. And if we're reading in the voltage, we would also expect inversely the force to go up. So with this data, we were able to implement a factor of safety from our literature review, like Stephanie mentioned, and the surgeons should aim for 1 to 3 newtons for a strong suture. On the bottom right-hand corner, you can also see our final prototype model, where you can see the 2 conductive cord sensors and 3 pressure sensors, which are also implemented with the red light and green light feedback, and our graphs display on the corresponding computer. Thank you very much.
Hi everyone, this is the robotic surgery training dome testing setup.
We utilize laparoscopic tools, including this entire setup, in order to view the dome and the suturing process. We also utilized robotic arms in order to simulate the robotic surgery. When we press on the sensor, the code reads in.
Also, when you press on the sensor, a red light shows if you don't have enough voltage for suturing, and green is good for suturing technique.
We also used the Open Camera app in order to view the dome in a surgical setting.
And lastly, we implemented Arduino connections through a MATLAB code in order so you can view the input that the voltage is reading from the sensors, as you can see when we touch it right there. Thank you.
Using the robotic arm, we were able to pull the suture wire through the incision, and when we pull, the conductive cord, the right conductive cord, is pulled towards the incision, and with that we get a voltage reading.
Okay, so here you can see we are demonstrating our ear suture pressure sensor. So Chloe is suturing, and you can see that our green light LED turns on when she places pressure. So that pressure is calculated by a factor, including a factor of safety, which gives us quantitative feedback for the surgeons to know how hard that they are pushing. We can show you the corresponding graphs as well, but here she's suturing as a surgeon would in their training. Okay, so here you can see our second pressure sensor, which we chose to mimic muscle fibers. So we're currently stitching on this platform. You can see again that the green light has turned on when she is pressing on it. So now it went back to red. The green light obviously means that it's a good suture, it's a strong suture, and the red just shows that there's not enough force for a tight closure of the skin. Okay, so here you can see is our last sensor that we're testing. You can see the green light hidden back here as she's pushing a lot of pressure on the suture pad. Once again, the light is turning from red to green with a strong stitch.
Hello, we are the benchtop battery assembly team. My name is Kristen Olliger, and I'm a computer science major.
My name is Sean Kane. I'm also a computer science major.
I'm Carlos Pons, computer science major.
Ryan Buten, computer science major.
Jake Cassidy, electrical engineering.
And together we will show you the solution that enhances the construction of lithium-ion batteries.
Once again, we are benchtop battery assembly, a group composed of 4 computer science students and 1 electrical engineer.
In this presentation, we would like to outline the problem of our project, the motivation behind why we're developing the solution that we are, the approach we took to that solution, and then a live demo at the end.
And now for the problem statement. Given a controlled environment, we seek to construct a system that would be able to determine the ideal environment for battery building, such that a battery's lifespan is maximized. This project shall design a closed-loop sensor system with a programmable logic controller, and integrated sensors that connect to a custom software system to track oxygen, temperature, and relative humidity. In addition, the project shall optimize the conditions for battery assembly based on acquired data regarding initial assembly conditions and battery lifespan.
The demand for optimal battery performance is higher than ever before. Many of today's cutting-edge technologies require some use of lithium-ion batteries, and as these technologies mature and become more mainstream, the demand for lithium will continue to rise. When exposed to oxygen, lithium quickly deteriorates, losing many of its desirable chemical properties. Our integrated system allows users to compare different conditions and ultimately optimize the battery assembly process.
The first motivation for this project was the belief that by having a smarter system with integrated software, battery assembly can undergo rapid prototyping. In turn, this leads to more innovation in the space and reduces costs. By predicting the performance of battery batches and keeping track of defects during a cell's lifetime, the system is actually able to learn from past mistakes and actively work to reduce them by alerting researchers to change conditions inside an isolated atmosphere. So the second motivation for this project was that this system will impact multiple key business sectors. The first being that this will economically disrupt battery production by offering a cheap way to R&D lithium-ion cells in an isolated atmosphere. Furthermore, there are lower barriers to entry as this system can be integrated with any pre-existing glove box hardware. The next big one would be the environment. Increased battery efficiency will make battery-powered modes of transportation more attractive, thus curbing greenhouse gas emissions. And touching on this, we feel that every sector will be impacted in the long run, as better batteries will transform our society from things like IoT devices to larger vehicles such as electric cars.
The tech stack that our team chose was NoSQL, OAS, Flask, and Vue. Open automation software provides a direct connection to the programmable logic controller. For our system's needs, MongoDB was chosen as the NoSQL, and the OAS offered built-in connection compatibility from our Allen Bradley PLC to our MongoDB. This allows data to be logged to the database from the PLC via the OAS. Essentially, the OAS is a wrapper object around the PLC. As a result, the technology stack now consists of an OAS for direct communication with the PLC, MongoDB database, Python backend using Flask, and a Vue frontend.
In order to determine the hardware needs for our project, we first considered the scope, which involved creating a control feedback system. This meant that we needed a device with signal processing and feedback capabilities. Although an Arduino would suffice for the needs of this project alone, the PLC is more beneficial in our case. First, the PLC is an industry-grade device that is designed to be interfaced with other industry-grade devices. There is no need for interfacing, as the PLC is able to provide the standard 24-volt DC for sensor operation. Also, we plan on passing this project down to mechanical engineers in the future. The ease of programming and ladder logic in visual graphics will allow for quicker understanding, as opposed to using lower-level languages like C. The modular nature of the PLC will allow for future project expansions, creating a more scalable system. Finally, the Allen Bradley PLC shares a similar software to that of the HMI. This compatibility will limit the need for debugging and interfacing two unique softwares.
Now to talk about the design approach. An analysis of the literature identified that there was a lack of real-time variable analysis within glove box systems. So our method really showed that the impact of the lack of data within the field was that it restricted the efficiency of the overall battery assembly. So now our original design approach had a software-first perspective, and the rigor of our research methodology is shown through numerous articles in which the team analyzed.
We dedicated a lot of time and effort to the validation of our system to ensure smooth operation and functionality. Allen Bradley's Connected Components Workbench allowed us to simulate our PLC program before installing it to the hardware itself. Analysis was performed to ensure that all hardware and software components were compatible. Although validation is important, the agility of our team to adjust quickly and effectively allowed us to be successful. The scope of this project initially contained 4 mechanical engineers, but we were able to create a robust system with our electrical and software expertise. The results were fantastic. The images on the right-hand side of this slide show the user interface in which the data is being streamed live during system operation. We ran into many challenges along the way, and that will be discussed throughout our following demo.
All right, welcome to our demo, guys. And we're gonna bring up a close look of the PLC and kind of show you what's going on here. So as you can see, this blinking green light right here, that just shows that the PLC's on and ready to go. This right here is actually a voltage converter, so it takes a 120 volt signal from the wall, like any standard outlet, and converts it to 24 volts, which is then used to power the whole system and distributed to the other sensors connected to power those. Right here, you can see channel 0 is also activated. That's actually channel 1 of our dual temp and humidity sensor, which is over here. Channel 1 is the input 1 on the PLC is connected to channel 2 of our dual temp sensor, so that's actually taking in the relative humidity readings. And what this is doing right here is this is actually sensing the relative humidity and temperature live in the form of a 0 to 10 volt analog signal. This is then being sent and communicated with our PLC and then sent via Ethernet to the MongoDB, which is then what we'll talk about in a few seconds.
So to give a little bit of context about what's going on with the sensor readings and how it's going to our backend database. So we have a analog voltage reader. Here is the sensor, and the flow of data is going to the PLC. And then as it's transmitted over Ethernet, it's hooked into our connected components workbench, and we use ladder logic to convert that analog data into readable human data. And then what we have behind me is a Python script running as a microservice. And what it's doing is it's converting that data into a JSON object. And from there, we can upload it to our database.
All right, so now as you can see on our application, which pulls the data directly from the database, you can see in the room we're reading 42% humidity, and our measurement's just slightly off because the humidity sensor is designed for low humidity, so its degree of error increases as the humidity increases. Our temperature is right on par though, 24 degrees Celsius, and we're at 23.58. So slight degree of error, but it's still within our threshold that we deem appropriate. And so that's why both values are labeled as true and acceptable. And on top of that, what we're doing here is we're grabbing the time frame of when the data is collected so that we know if the real-time data analysis is off or not. So this application right now can be accessed through laptop, iPad, iPhone, or whatever service you need, and we have a login for security. In addition to that, our database has security measures in place. And so this is how the user will be able to monitor what is actually going on within the glove box.
And so our ultimate plan with our system here is to integrate it into a glove box that's used in industry or for advisors' use. This would allow for the utilization of our database as it is here. And now Ryan will talk more to what our future goal is for our user interface.
So for the user interface too, we want to add components such as battery cells, which are developed within these glove boxes, and give statistics and data analysis. That way the user can understand how the batteries perform over time. And then in addition to this, we want to put a lot of the software components in the cloud service in order to increase system robustness. That way it's not just one desktop within the lab. And this as well will allow for the database and our software system to get data from multiple glove boxes at the same time.
Hi, we are the LiDAR car group. I'm Beatriz Guevara and I'm a computer science.
My name is Eric Ruilova and I'm a computer science major.
My name is Taeyoung Kim. I'm an electrical engineer.
My name is Jesse Vayo. I'm a mechanical engineer.
My name is Samuel Santos, mechanical engineer. The problem we sought to seek was to create a cheap robotic car that uses LiDAR.
The main problem we were trying to solve with our LiDAR project was to create a test bench so that both STEM students and researchers can learn how to properly use and understand LiDAR. As an emerging technology, it is becoming increasingly important for those in the STEM fields to understand how it works, and our car project fulfills this niche that has been missing in the market for this whole time. As all industries move towards a higher level of autonomy, LiDAR is quickly becoming the standard in terms of sensors that can collect both visual and spatial information. The difficulty then comes with teaching others how to understand and apply this data, and this is where our project comes in, an easy, accessible way to enter into this new field of data and information.
We are interested in solving this problem by making LiDAR technology more accessible and easier to learn in a fun way. Students, researchers, and professors will be able to work on a small car that will provide them with valuable experience that involves and combines three of the engineering branches: mechanical, electrical, and software engineering. The open source code used in the LiDAR card is just a start point. Users will be able to expand their coding experience and knowledge by modifying it and adding a wide range of possible maneuvers, and share them with other users. That way, the code will be constantly evolving.
Another motivation for our LiDAR car is to have an impact on younger students and hopefully trigger their curiosity in the STEM field. By keeping our costs down, we hope that our product will be easily accessible to teachers and students. By using off-the-shelf parts like Arduinos, our project can be modified and easily expanded upon. Furthermore, this project can be used as a test bench to gain hands-on experience with LiDAR and can be expanded upon by independent researchers or engineers.
Our approach to this design features a thermoformed frame that is enforced with a 3D printed support beam. Our frame, as seen in the bottom two photos, is designed specifically to fit our required components, meaning that our design is directly related to how we want our car to function, and if the components change, then so does our model. The main components required right now are a LiDAR sensor, servo motors, an Arduino Uno, and 4 batteries. In order to make this design, we needed knowledge of a thermoforming machine and casting, and when we obtained this knowledge, draft angles were used for the easy removal of the mold from the thermoforming machine, as well as the frame was featured with stringers for added rigidity, in addition to our reinforced support beam.
The way that we approached in making our vehicle was to have the car be able to go forward, stop at an obstacle, and scan around before turning. The code is made so that when the LiDAR detects something in a close proximity, the wheels will stop moving and will trigger the front servo to turn and scan for side obstacles. Then it will find the direction that is free and turn in the direction and move forward. If the car can't turn anywhere, the car will go backwards and attempt to free itself. The first picture on the left shows what the LiDAR is detecting and feeding back to the computer. As you can see from the picture, the distance is measured in millimeters. This data collection is important because this is the only way we can accurately tell the distance. The next picture to the right shows the LiDAR attached to the front servo. As you will see in the demo later, the LiDAR on the servo will turn 180 degrees to detect any obstacles on each side.
We're the microbioreactor group, and we're all mechanical engineers. My name is Erin Harvey.
My name is Caroline Ken.
My name is Garfield Curtis Jr.
My name is Wachpi Berkeley. Our project is aimed at designing 3D chambers for drug testing in the medical industry, ultimately to reduce the cost of drugs and cellular analysis.
For the duration of our project, we were advised by Dr. Sundaram. Our problem statement involves the need to make cellular growth analysis more affordable in order to reduce testing time and environmental waste. Constraints include working around biocompatible standards with a low environmental footprint. Our solution to this is an additively manufactured biodegradable microarray that is automated using software to speed up cellular analysis. Our motivation is to find efficient methods of research in the pharmaceutical industry, along with discovering more sophisticated ways to test drug effects on human tissue. Our array will contribute to future drug prices, testing timelines, and opportunities for other applications within healthcare and medical labs.
When approaching our project, our first step was to do background research on existing bioreactor arrays and see how we could differentiate ours from others. We noticed that none of the ones we were researching had individual controlled flow to each chamber. This is what we decided would differentiate ours and make it unique, so we wanted to have an array with multiple reaction chambers where the flow could be controlled to whichever one the user chooses. Another unique feature we wanted to have was making the array fully automated. There are flow diverters that are controlled by motors, so the user doesn't have to manually open and close each chamber. To do that, we use Arduino code. By having this unique modular approach, the user can add as many chambers as needed, which is the final factor that made our product so unique and different from others. For material, we decided to 3D print our array so that our product would be cost efficient and biodegradable.
For our design approach, we wanted to feature a compact design where all the components will be in a single unit. The figure below shows the station with the three motors mounted on top. The motors connect to the switches through a shaft, and each switch sits in the middle of a reactor. So the reactor on the bottom features a 3-chamber design, with each chamber having a separate cell under analysis. Each chamber features a fluid design where the switch controls whether the fluid goes into the reaction chamber and affects the cells under analysis. And the exit and inlet valves connect to a pump that can be used to create pressure to allow the fluid to flow through the design. Figure A is a single reactor module. The middle features 2 concentric circles, which is where the switch is going to sit on. And in the middle will be where you place a scaffold with the cells. Around the circles is the bypass valves, where the fluid will be channeled to in the event that the switch in the middle is closed. That way, the cells in the reaction chamber in the middle would not receive the fluid, and the fluid will bypass from the inlet to the next chamber. On the right is a 3-set array featuring 3 chambers. In the middle is where I said before, the cells will sit, which is colored in blue, and the switches move around it to control the fluid flow.
After looking at the SolidWorks models, here we have the actual 3D printed prototype of our design. On the left-hand figure A, we have the final prototype of the 3D printed array with the fluid diverters in each chamber. One on the left is being pointed to a chamber that would be open where the fluid would flow directly through the tissue scaffold. And the second chamber is closed where the fluid would take the paths around the sides of the chamber and bypass the tissue scaffold. On the right-hand side, figure B, we have the complete setup where the array is mounted in the station with the servo motors on top to control the positions of the fluid diverters. In our last figure 4, we have the final setup of our entire project. So A is pointing to the 3 servo motors that are connected to the chambers and controlling the positions of the fluid diverters, whether the fluid flows directly through or around the sides. B is pointing to the array and mounted into the station. C is pointing to the peristaltic pump, which controls the pressure of the fluid that is flowing through. D is pointing to the Arduino code, which is connected to a computer, and that is indicating the position of the switch, so the motor can automatically control that. E is pointing to the battery, which powers the servo motors. And lastly, F is pointing to the tubing that connects the drug and flows it through the array.
Okay, so this is our entire setup for the microbioreactor array for tissue engineering. So from left to right, I'll kind of go through the entire setup. We have the peristaltic pump here on the left, which has the input, which is where the fluid comes from, has the output, which flows directly to the 3-chamber array we have here, which is inside of the 3D printed station as well. There's 3 servo motors attached to each chamber individually, and what those do is they control the positions of the switch. And you'll see that as we go through the demo. The output goes into the speaker here, but these are the connections for all the servo motors. We have the breadboard and the Arduino board here. So we have the power source on this side, and we have the ground on this side, which these are all connected to the DC power voltage source. And we use the DC power, but it can easily be replaced by a battery to make it more transportable. We have the Arduino board then connected to the computer, which shows the Arduino code.
So the Arduino code is a simple for loop that changes the servo motor position from 0 to 180 with a delay of 10 seconds. So we attached each one to the Arduino pins. You can easily switch these angles to lower angles and can change the delay time, which makes this more versatile, and you can program it to do however you want it to rotate. But it's a very simple code. It's about 10 lines, and yeah, we're gonna run it now and see how it works. So as you see, the switches turn 180, then they spin in the other direction at 180 degrees. You can always change that to 30, 90, depending on how you want the rate of fluid flow in the chambers. We'll recommend about 90 degrees on each side with any delay you wish to put it. You can also cut off the code to stop the fluid flow. So with that in place, we're gonna see how the pump flows the fluid through the chambers.
So I'm going to turn the pump on all the way to its maximum potential, and you'll see the water flow through down through the array, and it will go through the array based on depending on the switch positions.
Hi, our project is end-to-end wireless communication using FPGA and various digital modulation techniques.
We are a team of all electrical engineers, and our names are Ali Alrawanduzi,
Shamrock Herrera,
John Dowling, John Fee,
Costa Caldaris.
and our project seeks to expedite the process of teaching and designing communication systems for educational and teaching purposes.
Designing and developing a communication system is complex. Our project seeks to create a wireless communication system that uses different digital modulation and demodulation schemes. These are required for the software-defined radio. Specifically, we are using BPSK and QPSK modulations. We do this through industry-standard field-programmable gate array Xilinx Z boards. We also use MATLAB to simulate the system and generate HDL code for the FPGA. Due to the complexity, importance, and developmental rate of communication engineering, there is a need for well-trained engineers. Hence, a PCB using an analog amplifier IC that demonstrates different modulation schemes was also created. An antenna was designed to transmit these modulations in an unlicensed band of 433 MHz. Our work provides a solution that helps students learn and understand the fabrication and development of communication system. Our project uses MATLAB and Simulink toolboxes for simulating communication systems, ANSYS software for simulating antennas, and the Z-board to transmit and receive modulated signals.
The Internet of Things is present in everyday consumer electronic products. IoT utilizes sensors to handle and process wirelessly transmitted data. Our team has learned to build a communication system and uses industry standard hardware and software. This hands-on approach to communication engineering allows students to better understand signal modulation and various uses of FPGA circuit design, and thus prepare them for a career in wireless industry. Communication system implementation can be used for many purposes and is a powerful tool. This includes enhancing markets and wealth through connecting the world to disaster scenarios, where these skills are crucial to save and provide efficient and effective aid to affected areas. This aligns with the School of Engineering's mission statement, which is service to humanity.
The software side of our team uses the following: MATLAB Simulink add-on to simulate BPSK and QPSK modulation observing on MATLAB's digital scope, spectrum analyzer, and constellation blocks to view data input versus output. This comes with the added benefit of being able to generate HDL code through Simulink in order to allow for modulation at various frequencies. Next, Vivado software is used to upload code onto the Xilinx 7000 boards and to configure the board's outputs. The Xilinx SDK is used to convert C code to Verilog HDL and upload it through the UART connection ports on the Z board. The board to process the HDL code and respond by creating a serial output, which can then be read on the PuTTY serial monitor. This process will allow us to write sine wave and square wave generators that can enable the modulation techniques to be performed on the Z board.
The hardware side of the team used analog multiplier IC to create a circuit that will output BPSK and QPSK modulation schemes. We fabricated the PCB and tested it. We also simulated a suitable antenna that would be able to efficiently radiate at 433 MHz frequency using ANSIs. We chose a meander line type antenna with coplanar waveguide excitation for the antenna feed. The antenna is made of FR4 material with dimensions of 107, 35, and 1.2 millimeters. The antenna radiates at slightly higher frequency, which is still an unlicensed frequency band.
We now will demonstrate the simulated modulations on MATLAB, the PCB board that shows ASK, BPSK, and QPSK modulations, and the simple HDL code implementation of the Hello World onto the Z board.
Here we can see a Simulink simulation block diagram with a BPSK schematic. This model works by taking a message signal, which is binary, modulating it, and then multiplying it by a carrier sine wave signal. We can see the constellation oscilloscope and spectrum analyzer outputs here. Due to limited computation power, our carrier is 100 Hz and our signal is sampled once per frame. Following this, over here, we have the output signal if it was to be received before it was demodulated. This is simply done by multiplying the output signal by the carrier once more.
In the simulated QPSK transmission, we have a pseudo-noise or PN generator feeding into the QPSK HDL modulator modeling block. This signal is multiplied by a sine wave generator that creates a QPSK modulated sine wave signal. We can view the signal with a constellation diagram, a spectrum analyzer, and a digital oscilloscope. We can see the modulated peaks of the signal and the changing phases in the following graphs. These signals are ideal simulations and we should expect to see similar output signals in the real demonstrations.
Here we have an ASK modulation demonstration. We have a message signal of 25 kilohertz and a carrier signal of 250 kilohertz. If we see over here on the oscilloscope, we can see the zeros being represented by the flat voltages and the ones being represented by the voltages which are exactly the same as our carrier and message signals. We can use this potentiometer to fine-tune the modulation at different frequencies, and by turning this potentiometer we can see that over here on the oscilloscope that it is changing.
In this demonstration we have our BPSK modulation signal. We have a carrier signal of 100 kilohertz. We have the same exact circuit, which can be seen here, as our ASK signal. On the oscilloscope, measuring the output signal, which would be taken from this wire right here on this circuit. we can see that the output switches phases every time it shifts from a 1 to 0. In this last demonstration that we have our QPSK circuit, which multiplies the two output signals from both halves of the circuit. We have them summed in a summation amplifying circuit that multiplies 200 kilohertz BPSK signals into what we have as our QPSK signal. There are more frequent shifts in accordance with QPSK, as it shifts 4 times in the same period versus the BPSK's two phase shifts per signal. In this final example, I will be demonstrating how we use our Xilinx SDK software to upload a simple C code to our Zinc 7000Z board. The Zinc 7000Z board has all of its J11 to J7 pins grounded, which are the boot up cables, and we use these blue jumpers seen throughout this entire board to set up and allow for the configuration that we have. We have a JTAG cable connected to our Xilinx platform cable hub, and we have a micro USB connected to this from the Z board to my laptop, allowing me to run a simple Hello World C code that I can upload to the board, and we can see the output from the serial monitor. When I run this code, we can see that it compiles here. We can see all of the connections being processed, and it uploads the output here, displaying a hello world.
Hello everyone, we're the STEM Outreach Senior Design Group.
My name is Ina March and I'm an electrical engineering major. My name is Rachel Jacobson and I'm a computer science major.
I'm Prince Idol and I'm computer science.
My name is Tobenda Ugu and I am a biomedical engineering major.
I'm Chizim Zachuruko and I'm a biomedical engineering major.
I'm John Minogue, I'm an electrical engineering major. Our project is to bring athletes into the STEM field using biomechanics devices by performing a sports combine.
A recent NCAA study showed that 26% of college grads graduated with a degree in STEM, while that percentage was only 16% for student athletes. So our goal is to diversify the STEM pipeline by introducing STEM ideas to students. Current STEM outreach programs like science fairs and robotics clubs aren't actually catered to underrepresented student athletes. So therefore, by creating a sports combine, we'll be able to reach out to those underrepresented students. Our goal is to increase athletes' pursuit in STEM, and our future plans are to provide teachers with devices and instructions so they can cater these devices and systems in their own schools.
We are interested in diversifying the STEM pipeline because in today's society, STEM is an up-and-coming field of study that should represent people in different communities. One of our project goals is to assist in solving the problem of convenient sampling in biomechanics and engineering at large. There's barely any biomechanical data collected from underrepresented communities because most of the surveys are focused on college students and athletes or individuals from wealthy neighborhoods who attend properly funded schools or after-school programs. A concerning issue is that a lot of musculoskeletal diseases affect underrepresented communities, and without the proper outreach, people in these communities go unnoticed. Access to higher education will help spread this outreach, and we intend to pique the interest of youth through athletics. Generally, the lack of data from these underrepresented communities hinders treatment development. The aim of our project is to solve two basic issues: expand outreach efforts to include underserved communities and diversify biomechanical data, which will aid in research and treatment development.
In designing our 3 devices, there are 3 major areas we considered in terms of approach. The first is the manufacture of the casing. We decided to make use of 3D printing because it's a precise and accessible way of producing the casing with well-detailed measurements. We're able to distribute the design files to different schools and athletes who are able to 3D print the device and engage in conversation about the different parts of the device. The second part is the electrical. Arduino was chosen as a mode of circuitry as it is easier to find and cheaper in reducing cost of our device in general. The code is something that students can make use of and learn more about the biomechanics device. The parts used are LCD screen for display, force sensitive resistor for sensitive devices to force from push-up, Having an Arduino makes it possible for more interactions with youth athletes on the different possibilities in STEMs.
The images below show Arduino circuits for each device. Graphical user interface design in Python takes Arduino data and converts them into arrays based on each athletic test. Users then enter their own data into our application, and their scores are converted into percentiles based on a comparison of the Arduino data. These results are graphed in a radar plot.
As we were saying, we've created 3 different devices to run 4 different tests. The first one we'll present is the push-up counter, then we'll move on to the toe tapper, and then lastly, we'll talk about the photo gauge with the laser sensor.
This is our push-up sensor. This is used using an FSR. Every single time I press down my chest on the tennis ball then actuates against the FSR, counting a push-up. The test takes 30 seconds. I'll show you how it works now. As I reset the test, it counts down from 3, and then it beeps to start the test. Every single time I perform a push-up, it'll beep every single time I perform a push-up. As you can see, I just performed 5 push-ups. If you come here and look at this, the push-up number is 5. The time for the test is still going because it's a 30-second test. Once it hits 30 seconds, you'll hear it beep. That's the end of the test, and that's how the push-up counter works. This is our agility test. We put a soccer ball on top of our housing, and it does the same thing as our push-up sensor does. Inside of the housing right here on the edges will sit an FSR. Every single time that I touch my foot on top of the soccer ball, the FSR will once again count every single time I touch it. Every single time I touch it, it'll count, it'll count, it'll count. So I'll perform the speed of the test right now as somebody who's doing it with speed. We'll do it like this. And every single time I tap the ball, it'll tap down on the FSR and count. The test, once again, will take 30 seconds. This is our photosensitive resistor for our speed and our agility test. Basically what happens is we have this side right here and a gate on the other side that shines a laser into the foil. The foil will reflect and hit our photosensitive resistor. What the test will do is it'll count every single time that there's a drop in the light that's received by the photosensitive resistor. So when someone passes the gate. So as you can see what just happened in the video there, every single time I pass the gate, there's a huge drop in the photosensitive resistor. That's what we're detecting. So you'll run a 5-10-5 drill and just a simple down and back drill, and it'll test the speed that it took for that person to complete that drill. So now you can see if you look at the serial plotter on our Arduino code, it'll start the time when I'm standing right here at the gate when there's that first drop, and then I'll go and it'll raise all the way back up, and then when I come back to the gate, it'll drop again. It'll stop the time for the test will be completed, and that'll be their time for their speed and their agility test.
After user data is collected through each device with the Arduinos, users will have the opportunity to enter their own personal scores into our application. For example, user 2437 scored 8 on the push-up counter, received a vertical score of 27.5, a quickness test of 35.5, and then agility 3 and speed 2. When their scores are entered, they produce a radar plot that is opened externally. The scores that you see on the radar plot are determined based on percentiles, which are compared from the Combine event that day.
This concludes our presentation. Thank you for watching. We'll stick around for questions.
We are the Community Situated Biomechanics Group. I'm Gabby Romero, and I'm a mechanical engineer on the team.
I'm Joe Viali, I'm also a mechanical engineer.
I'm Avery Nocella, I'm a computer science major.
I'm Caroline Nielsen, I'm a computer science major.
I'm Butch Mega, I'm an electrical engineering major.
I'm Jack Delva, I'm a biomedical engineer, and due to the seriousness of musculoskeletal injuries, we have designed a mobile biomechanical device to measure Achilles tendon rupture for at-risk people.
For this presentation, we will go over our problem statement, our motivation for this project, the design we came up with in order to solve our problem, and lastly, a demonstration of our device. Our team was tasked with designing a mobile biomechanical device that can measure the Achilles tendon before a rupture or tear occurs for at-risk people such as athletes or older people. As you can see to the right, the main parts of the calf are the soleus and gastrocnemius, as well as the Achilles tendon, which connects the calf muscles to the heel bone. With this muscle, you could be diagnosed with tendinitis, tendinosis, or a complete rupture. The problem is that once the injury happens, it becomes very painful for the person to walk, and without proper treatment, even just walking around can worsen the injury. This is why we want to know before the injury occurs in order to properly understand the Achilles tendon and to treat it more efficiently.
Knowing the seriousness of this type of injury has been our main motivation for completing this project. This can affect two main groups of people. Overuse and improper stretching of the muscles are common causes of this injury in athletes, where older people's muscles and bones become more fragile as they age, making it easier for them to be injured. These two types of people are a main source of motivation. Being able to help decrease the injuries for the Achilles will significantly help the public. This will raise awareness about the seriousness of an Achilles tendon tear, which can influence how researchers, doctors, and physicians examine the injury. We want a device that can be used outside of a laboratory, so it'll be more practical towards our target audience.
For the hardware approach, the original design that we are working from was more of a horizontal design that would be placed on the ground, and then the individual would place their foot on the foot plate and push. Issues with this device was that it had too many constraints causing stiffer movement, as well as it didn't have a consistent original position. Coming from the original device, one of our designs was to have the individual lay stomach down on a table and push a pedal with their foot. We realized that this wasn't ideal because we would always need a table and because it would be quite big. That's when we came up with the final design of having an individual sitting down where they would only need a chair, as well as this would allow them to have a general starting position. We chose a system with a load cell damper and slider assembly because it would allow the individual to push against the load cell to get results. The slider assembly acts as a device for the individual to push against without hurting themselves, as it is easy to move assuming there is no friction. The damper can either lower or increase the strength needed to push the slider assembly, and it also allows there to be some force against the individual's push so that they are not just pushing against the load cell with no force. The load cell allows us to record and obtain the values from the force applied by the individual with the slider assembly, and then connects to an Arduino and then the interface. Lastly, we would like to give credit to Dominic Figueredo for reviewing our final design and for helping us with the build by cutting and adjusting our materials.
Over the course of this project, we have gone through a numerous amount of designs based off of, mechanical design or, either whether a circuit we built didn't work or not. This present design we have basically has about 6 components. The first one being the wires, the second one being the breadboard. We used a half-sized breadboard, which measures about 1.8 inches to 1.4 inches. The third one is the HX711 load cell amplifier. The fourth one is the TAS501 S-shaped load cell. Originally, we had used the disc-shaped TAS606 load cell because it was easier to mount. But since our mechanical team had come up with different designs, we were able to use the S-shape because it works better with that design, and we also found it to be easier to calibrate. The fifth component is the Arduino Uno, which is the microcontroller we used to connect to a graphic user interface. In this case, could be a laptop or an iPad. The sixth and final component is basically what we use to house all these other components. So we decided to 3D print a box which houses all the components in one, and that is our circuit.
Lastly, for the computational aspect, we used a Python application that connects to the Arduino through serial to track the live data from the load cell. To start, we decided to complete a concept collection or a design matrix to decide what language we were going to code the application in. As seen in the chart on the left, Python was the language that we decided to use out of Java and MATLAB. In order for us to gain experience with coding with live data, the first test we did was with a potentiometer and a force plate. We tested the code last semester and now have the code for the load cell on the ISO damping dynamometer. We kept the same code that we used last semester but added a few components to the application.
We had to make edits to the Arduino code since we had it coded a certain way to connect to the Python application. So we had to add the load cell code in that the electrical engineers worked on into our Arduino code so that we were able to connect the Arduino through serial to the Python application. You can see the application on the left side. There is also a start button that starts the graph and establishes the connection between the Arduino and the computer. To stop the graph, the user would have to press the start button again, and the start button would turn into a stop button when the user initially clicked it. The user can also save the data by pressing the save button, and the data will save to the computer in the form of a CSV file, or on some computers as an Excel file. The user can clear the data by pressing the clear button, which will restart the data collection. The speed of the live data display is controlled by the number next to the send button. It is in milliseconds, so if you want to speed up the output data, type in a smaller number like 100 and press send. The min and max y values on the right can only be used when the application has finished running. This portion allows the user to zoom in on a specific area of data by adjusting the min and max y values. The application is being deployed locally for now, so we are going to be the ones running the application and conducting the testing for right now. We have never had coding experience with tracking live data from a device, so we were worried that it was going to affect the results we would receive from the code. So we had help from YouTube videos and other websites such as Stack Overflow to help us gain a better understanding of how to track live data via a Python application connected to Arduino through serial.
In order to validate that our device is in sufficient condition to be sent to schools, coaches, and other users, we tested and evaluated our isokinetic dynamometer on ourselves. Each member of our team ranges in height and different shoe sizes, allowing for us to test whether or not our design is fit for all heights. Through this test, we were able to determine that the maximum height would have to be adjusted in order to make the device user-friendly. This test was further evaluated at the Innovative Research Symposium. We had several people approach our booth, including a member of the Fairfield men's basketball team, whose height was above 6 foot. We learned from this event that we would have to make further adjustments to the final height in the design in order to make this fit for someone of that height. We were also able to determine a way to test for those who are taller by having them place their foot on the ground instead of on the metal bar. The symposium also gave our team a great chance to test the best footwear to use with the isokinetic dynamometer, as it was determined that a flat-based sneaker was the best fit. The software side of the project was tested with several devices to ensure the understanding of the software how-to manual. After downloading the software which was created, we ensured that the interface was user-friendly and easy to turn on, shut off, and save and clear information which was recorded. Below is a graphic example from the interface. As a team, we set firm deadlines and met each week to discuss what we had accomplished, as well as any issues we may have encountered. These deadlines help the team to stay on track for the end of semester goal with our device. With these deadlines, the team was able to make several prototypes and designs before settling on our current device.
Hello everyone, we are the Java App Store team and we are all computer science major students. My name is Lambui.
I'm Sachin Verma. Maz Vora.
I'm Ricky Jagru.
I'm Harshal Khatri. I'm Rocky Dulhaq.
The problem is Java app developers have no place to monetize and deploy their applications. That is, until now. Introducing the Java App Store.
Given the lack of a platform for Java developers to monetize their work, we seek to create such a place where Java developers can easily deploy their applications to make them accessible to the public and potentially earn money through them. In order to avoid malicious use of applications, however, we will also have these developers subjected to an identity verification process. Only then will we publish their applications. We are interested in solving the problem that Java developers have which is that they do not have a centralized location to publish their apps on an app store. This is detrimental considering there are 3 to 4 times as many Java developers as there are iOS developers, and iOS has one of the largest app stores. This is what motivated us to create a Java app store that allows Java developers to easily publish their apps to our store with very minimal cost, without restrictions placed upon them. This application will make the app development industry more competitive because Java developers will now be able to play a much larger role than ever before. Others can take this work forward by having Java developers subscribe to this platform and deploy their apps, as well as having desktop app enthusiasts download apps from this store onto their devices.
Our current implementation of the Java App Store consists of collecting applications into a centralized repository to allow customers to directly browse and download applications. Customers have the freedom to choose whichever and however many applications they want to download without having to deal with download managers or risky executable files. Our implementation directly addresses 2 realistic constraints pertinent to our project. User safety is emphasized as developers seeking to upload their applications onto our platform must not only have their applications vetted by us, but they must confirm their identity by visiting a notary. We will not allow any risky applications to be downloaded into our repository, and we will periodically verify that the repository's existing applications are secure. This implementation will allow for easy evaluation of the App Store's repository because all of the apps are in a centralized location. Further, our repository model directly limits our costs, as customers are able to download applications directly at virtually no cost to us, even if multiple applications are downloaded. Not having to manage many user accounts or download managers will limit the Java App Store's overhead, as we will not have to spend as much to maintain such things. Of course, our platform considered multiple approaches before choosing the current implementation. We wanted to pursue using Java Web Start from Oracle, but we found out that that service is deprecated and totally unavailable in recent Java versions. We would not want to gatekeep developers on different versions of Java seeking to use our platform, so we did not go with this approach. We then thought of creating our own deployment application, but we decided against this because it would require users to take the additional step of downloading this application. We would also have to take time to ensure that this application is bug-free, and funds would have to be diverted away from a platform that already works. Another feature we thought to implement was to allow users to create accounts and log in to deploy applications. We decided not to proceed with this because we do not have the infrastructure, as we are still in the early stages and looking for more developers to join us. We would rather these developers contact us directly to ensure that we could fully identify and audit them. We also thought of allowing developers to directly upload executable or .exe files. This approach has 2 drawbacks, however. The first is that users on Mac would not be able to use these applications. The other is that this is a security risk, as executable files are difficult to audit due to their nature. But once we had a working implementation of the Java App Store, it was time to go to market. To test if customers were willing to use our platform, we launched campaigns on Kickstarter and Indiegogo. Unfortunately, these campaigns did not raise the funds that we hoped they would, but they were not without merit. Interacting with potential customers allowed us to redesign the platform and tailor it to non-developers. We were able to create a new front page for the Java App Store. It's on the right, not too shabby, right? Here is our current deployment of the Java App Store.
And here are some Java applications that are available right now on our App Store.
Well, that's all we have for this presentation. We hope you enjoyed what you saw in this video, so thank you so much for watching.
Hi, we're Team Scaffolds Containing Polymer and Graphene Oxide for applications in biomedical engineering. My name is Keely. I'm a biomedical engineering student.
My name is Alex Mayer. I'm a biomedical engineering student.
Back to Molsina, and I'm a CS major.
I'm Emery Aiden, and I'm a CS major.
The purpose of our group is to create and characterize polymer graphene oxide nanomaterial for applications in biomedical engineering.
Here are the name of each of our group members: Emery, Key, Alexander, Vivek, and this is our topic: polymer graphene oxide nanocomposites for applications in biomedical engineering.
Our outline consists of the problem statement, approach, experimental setups, and results. Our problem statement consists of currently wound dressing uses cloth material. The nature of the nanomaterials we are developing can encourage healing at a greater rate than the traditional cloth material. This topic has only been explored in energy storage area, but exhibits some characteristics such as lightweight, elasticity, compressibility, formability, and softness that can be useful for applications in biomedical engineering. We are not targeting any specific area currently. We are studying the characteristics of the scaffolds to see whether it is safe and biocompatible.
Our approach included first electrospinning, GEO, and PVA, and then we electropolymerized the electrospun GEO PVA material with pyrrole, and then we studied the characteristics of the scaffolds containing GEO PVA and pyrrole using scanning electron microscopy, otherwise known as SEM, and UV visible spectroscopy.
This image shows the electrospinning process. In the electrospinning process, a solution of PVA and GEO was placed into the syringe on the bottom right. The solution is pushed through the tube over the course of several hours and sprayed out the nozzle towards the collecting plate. An electrical field is generated in the air between the nozzle and the plate, which aligns the PVA monomers into polymer nanofibers. This creates the nanofiber mesh with graphene oxide flakes as the base for our material.
The electropolymerization method that we used was silic photometry, as shown in the picture above. There are 3 electrodes: the counter, working, and reference electrodes, and I also labeled that. We used the glassy carbon plate as the working electrode, and we tap a piece of electrode spun GO and PVA on the glassy carbon electrode and immersed it in the pyrrole solution to create a PVO, GO, and pyrrole scaffold. We later used the scaffold to image it to see how much polymers that covers the scaffold through SEM and test whether or not there was any GO releasing from the scaffold through UV vis.
In the slides here, you can see the data that we obtained from SEM, referred to as scanning electron microscopy. We do so to calculate the diameter of the nanomaterials that we have manufactured. Here are some of the images that you see on the screen from the SEM, showing the morphology of the individual nanofibers and the scaffold itself. The way SEM works is the machine focuses beam of electrons and we get an image of our nanomaterial. This allows us to determine the presence, size, and configuration of the nanofibers of the material, and also it helps us to identify if GEO, which is graphene oxide, is bound to our scaffold. The results that we obtain show that the nanofibers that we obtain, some of them are beaded, have large balls connecting the strands. While this is not an ideal material that we want, because these beads that we obtained didn't stretch out into nanofibers, but it is not detriment to the overall material that we have prepared. So we are also able to confirm the presence of graphene oxide that had bound to the nanofiber scaffold to this SEM analysis. The images that you see on the screen, the first one being PVA, GEO, and polypyrrole. The second one is PVA, GEO, polypyrrole, and on aluminum. The other images are similar, showing the nanomaterial on PVA on aluminum, PVA on parchment paper, and the final slide showing PVA polypyrrole on parchment paper. We have a graph showing the frequency and the bin. Frequency here referring to the number of fibers, and the bin referring to the dimension of the nanofibers.
This slide shows the results for the UV vis spectroscopy. It's also known as the ultraviolet visible spectroscopy test, which was done by leaving the completed material in water for 5 minutes, 12 times. Each of these 12 samples were tested against control trials for the 3 materials utilized in the final material. The spike in wavelength shows the presence of the material in the scanner. The results show that there was no contamination in the water for the 12 trials from any of the 3 materials. The trials 4 through 15 were showing a range below 0 intensity, whereas the controls spiked in intensity at the beginning of the wavelengths, showing the presence of the three materials. In this video, you can see a demonstration of how the electrospinning process works. First, a solution is placed into this syringe, which in our case contained polyvinyl alcohol and graphene oxide. This solution is then slowly pushed through this tube over the course of hours and sprayed out of a nozzle towards the collecting area. In this particular video, the collecting area is a rolling drum, which allows the electrospun nanofibrous strands to come out in the same orientation. However, in our case, we wanted randomly aligned nanofibrous strands in order to have a larger surface area, which could help encourage cell growth. There is an electric charge in the air between the nozzle and the collecting plate, which you can see attracts the material in the fluid towards the collecting plate. This is what helps create the nanofibrous strands and align the polymers in the correct orientation.
My name is Sean Feeney. I'm a mechanical engineering major.
I'm Kevin Feeney. I'm a mechanical engineering major.
I'm Kevin McDonald, mechanical engineering major.
I'm Owen Kinney, mechanical engineering major.
My name is Martin Carraro. I'm a mechanical engineering major.
I'm Bashir Khalil. I'm computer science major.
I'm Matt Romatello. I'm a computer science major.
And I'm Aitan Mushayev. I'm an electrical engineering major. We are all the RBC lubrication team. The purpose of our project is to build a device that automatically lubricates a bearing using Molykote grease in under 7 seconds to take the human factor out of the process.
All right, so this is our senior design presentation of the automated grease dispensing equipment in collaboration with RBC Heim Bearings, and there's all of our names, advisors, instructors, mentors, and funding. So the problem that we have to address is eliminate manual grease processing at RBC Bearings. We started from the design process all the way to creating a fully functional grease dispensing system. We wanted to also apply this to different size bearings. RBC manufactures different types, and we also wanted to reduce the lubrication time by around 50%. So our motivation behind this project was to increase the production rates by creating this automated system. We also had to keep in mind that we would be reducing the human safety aspect of it, as reducing the human hands that come in contact with the compression machines at RBC. And we also wanted to enhance the ease of possible new employees training by having a fully automated system instead of having it manual.
So for the methodology for our project, we had to select a grease pump with tubing to transfer the grease to the part itself, develop a gripper to grease the bearing, provide a one-axis motion using a linear actuator, control the whole process using a PLC, HMI, and wiring, design and fabricate and assemble all the components for a complete product. So this is the final project itself. It consisted of a linear actuator, extruded T-slot aluminum base, a gripper, HMI, control box, grease pump, and grease container.
This is the process flow diagram for just the greasing process. So when the person clicks start on the HMI, this will enable linear actuator. And when the limit switch is activated, the pump will purge for 1 second. The pump will then reset. The linear actuator forward program will be enabled. And this will end up driving the linear actuator forward. And once that is completed, it'll drive it backwards, and that will complete the cycle. Linear actuator will reset, and this will count the part and reset the whole process back to the beginning.
So for the grease pump and tubing, to first find the correct grease pump, we had to find a strong enough pump using the NLGI grade number of 2. And then we chose the Lincoln Lubrication high pressure grease pump, which is an air pressure powered pump. And we chose 6 millimeter outer diameter tubing as to not filter out the metal flakes in the grease. And we had, it connects to 2 grease dispensing rollers.
So here is the gripper design that we made on SolidWorks that gets attached to the linear actuator, and it's connected to the base and the grease dispensers on the top of it, and its dimensions are shown here. Here's the gripper exploded view, so we can see how all the parts are fitting to the assembly. It has a screw, gripper arms, grease dispensers, the spring, the base, and the nut to hold the screw together.
Here we have the wired components of the device. The top level is going to be all the components that are inside the control box, and the bottom levels are the components that are outside of it. Here's a more specific wiring diagram of all of the components within the control box.
Here's a screenshot of the HMI screen we created using software Seymour. As you can see, there's a start button, a part counter for the amount of bearings we have, the pumpers and the status, reset counter, the home screen, and the e-stop button. And on the right, you can see the indicators of the pump, actuator, and the alarm. When they're green, they're on, and when they're off, they're red.
This is our final product with the gripper on the left. It was 3D printed, the control panel that's completely finished, and the full assembly on the right. In conclusion, our device ended up successfully lubricating the circumference of the bearing, and we reduced the lubrication time by 85%, which met our goal of reducing it by 50%. The programming and the process works consistently through the PLC system, and RBC Heim Bearings Corporation now owns the device and will integrate it into their production process. We'd like to thank RBC Heim for funding the Hardeman Grant, Garrett Lawler, Alex Kozhizek, Matthew Schmidt, Jesse Sterna, and Derek Favre for helping us through this project. So right there, you can see that there's an ungreased bearing, and that's what we're attempting to grease right now. Let me back up here, focus on the HMI. Currently, it's stopped right now, so what we're going to do is deactivate that stop button. Again, the limit switch is going to be activated when the rotary press rotates. The pedestal is going to hit it. First, obviously, it's not going to work now because it's not started. So once I press start, now it's running. Give it a second for the program to go. Now I'm going to hit the limit switch, and it's going to go forward and hit the bearing. So get a view of the going onto the bearing. And then it greases the bearing. And right there you can see with that one thing, it completely greases it. Perfect.
Hello, we are the Solar Desalinator Senior Design Project Group. This is Justin Ormston, Mike O'Leary, Enrique Lopez. I'm Charles Lewis. This is Vin Tiernan and Sean Ormiston. We are mechanical engineers, and our project is to make an affordable solar desalinator for less privileged areas that are coastal so that they can have clean water more readily available to them.
With 1 in 3 people around the world not having access to safe drinking water, our team aimed to create a device that converts seawater into safe drinking water. Many pre-existing desalinators are financially out of reach and impractical for thousands of communities around the world. As a result, we've designed a portable and solar-powered desalinator that can be applied in struggling communities all around the globe.
With over 800 million people around the world without access to fresh water, the need to provide clean drinking water to all has become the focus for many engineers. Due to high salt content, more than 97% of Earth's water is undrinkable. Desalination is the process that removes salt and minerals from water, and developing a system for desalination will help convert majority of Earth's undrinkable water to fresh drinking water. However, many desalinators are often inaccessible to much of the world, specifically third world countries, due to the economical and technological restraints. Solar desalinators utilize solar energy to produce fresh water, making them more accessible to areas that lack electricity. Unfortunately, many existing solar desalinators require a large capital investment. Our goal is to design and produce a compact, portable, and simplistic solar desalinator that can function with minimal maintenance. Our easy-to-use design makes our product appealing for global use and help solve the global water crisis. As a team, we believe that the global issue of supplying clean, drinkable water needs to be resolved and are interested in doing our part to help those in need. The water and wastewater market is estimated to be roughly $211 billion by the end of 2025, growing at an annual rate of 6.5% since 2019. The growing market reflects the world's increasing desire to solve the global issue. Our goal is to further the world's progress in designing and developing suitable technology for providing clean water to those who lack access. Our team's knowledge of thermodynamics and fluid mechanics will aid
in the design process.
For our project, our initial approach was to research pre-existing desalinator units on the market and improve upon them. Our goal was to design 2 prototypes that are both portable and cost-effective. This involved designing the prototypes to operate with as little maintenance as possible and desalinate water strictly through the process of evaporation and condensation. By making 2 prototypes, we can test each of them and decide which one is the most effective and safest for application of supplying fresh drinking water. The first of the 2 designs we came up with consists of a set of rectangular-shaped containers with an acrylic pyramid to cover the open face of the container. The inside bin holds the salt water and the outside one holds the clean water that drips from the acrylic shield after evaporating due to solar energy. After it evaporates, it condenses on the top of the acrylic and drips down to be collected. Additional details are implemented, such as hinges that connect the side of the outside frame to the acrylic shield in order to open up and collect clean water. PVC pipes are used for the inflow of salt water as well as the outflow of brine once the water has evaporated. Our second design utilizes copper piping attached to a reflective shield. Solar energy is reflected off of the shield and into the copper pipe. Within the copper pipe, there is a channel of salt water, which will then be evaporated due to the increase in heat. Similar to our first design, the fresh water will condense on the inside of the outer pipe and will be collected for safe drinking. These copper pipes and reflective shields are connected in series in an attempt to maximize our output.
By the end of the first semester of our research, our team had accumulated enough money from various grants to upgrade our project to a final design by purchasing better equipment that would significantly produce more fresh water than our 2 preliminary designs.
For the new design approach, the system consists of filters, a series of tubes connected to the filtration system used for both inlet of salt water and outlet of fresh water, a sediment filters that captures the bigger particles, and a pump that provides enough pressure for the water to go through the whole system. For a more sustainable approach, a power supply is used in order to power up the entire system, which can be easily charged using the set of solar panels, making it use as little human input as possible while yielding optimal results.
For our project, we had to conduct several tests to understand the efficiency of our solar desalination unit. The salinity of seawater, which happens to be about 3.5%, was matched in our experiment. 5 gallons of salt water was pumped through the system, and the salinity of the output was recorded using a salinity meter. The water needed to be pumped through the system a total of 4 times before a sufficient amount of salt was removed. Additional data was collected, such as solar panel efficiency and battery usage.
For our project, we had to conduct several tests to understand the efficiency of our solar desalination unit. The first test conducted during the validation process involves testing how long it would take to charge the power supply using 2 solar panels. The data from this first test can be seen in the table below in 2 different types of weather. It is important to note that this test was conducted in the winter months. Solar panels produce 40 to 60% more energy in the summer months compared to winter months. Our next test involved evaluating how long the battery would last when powering the pump and reverse osmosis filter. Our data shows that 10% of the battery is used per 1 hour. Overall, the battery can last a full 10 hours before draining completely. With this data, we can conclude that on a sunny day, the solar panels will provide enough power to the battery to allow the system to run indefinitely until nighttime. This will be more evident in summer months when solar panels produce more efficiently. The last tests in the project focus on the conversion of salt water to fresh water. To mimic salt water, we mixed table salt with 5 gallons of water to produce salt water with a salinity concentration of 3.5%, which is the same salt concentration of seawater. This water was then forced through the filters and tested at the output. It's important to note that one run-through of the filters was not enough to remove all the salt content from the water, so we had to run the water through the system 4 times to remove nearly all of the salt content to produce fresh water. This data can be seen in the table below. Overall, our data shows that 10% of the battery is used in 1 hour. The battery can last a full 10 hours before draining completely. With this data, we can conclude that on a sunny day, the solar panels will provide enough power to the battery to allow the system to run indefinitely until nighttime. Also, it would take roughly 1 hour to produce 5 gallons of fresh water.
Hi, this is our team. We're the 3D printed heart vein system. My name's Ilan Fair and I'm a biomedical engineer.
My name is Joshua Harris and I'm the electrical engineering major on this team.
My name is Dragono and I am the bioengineering major.
And I'm Peter Gordon, I'm the mechanical engineering major. The purpose of our project is to be able to print the early stages of a heart. By printing the early stages of a heart, we can make more complex chambers and eventually print a whole heart with living cells.
This presentation consists of explaining the problem we have today regarding donor hearts and how we plan to fix it. We utilize cell culture methods, 3D bioprinters, and electric stimulus to create our device. Videos on the bioprinters and the electric stimulus are shown later on. The problem we face today is that as of October of 2021, 106,834 people who are in need of an organ transplant have already signed up for a transplant waiting list in America. Every 9 minutes, another person is added to this list. And on average, 17 people die each day waiting for an organ transplant, as the wait list is expected to take about 6 to 9 months. Of these patients, up to 50,000 of them are heart transplant candidates. Because of the severe organ scarcity, the healthcare professionals face the challenge of life and death. They have to decide who gets a heart transplant and who does not.
Manufacturing a potential heart replacement means that theoretically no one will have to wait 6 to 9 months for a donor transplant again. We want to save those lives by doing so and combining additive manufacturing technology with stem cell culture to develop a 3D bioprinted heart replacement. Cell culture is an essential process that generates a large amount of living cells, but it is expensive and time-consuming. It requires the use of specific environmental conditions, such as temperature, oxygen, humidity, and CO2 levels. The cells also require a number of substances and materials, like cell media, that promote intercellular signaling, which is required for cell growth, differentiation, and proliferation. The chosen cell line, H9C2, is a skeletal muscle-like subclone derived from an embryonic BD1X rat heart tissue. After the cell's rate of development and proliferation slows, they are visually analyzed through microscopy, then removed from the culture dish, cleaned and separated from the cell media before they are mixed with the 3D printer's biogel.
Looking at the bioprinting process of this project, we use 2 different types of printers all year long. We use the BioX and the LumenX. For our material, we look to use a GELMA-based bioink. What the GELMA allows us to do, it allows us to print standalone structures and scaffolds without the use of a mold. Molds can cause damage to the material, so we try to avoid that. Then, for our GELMA, we also needed to have laminin and fibrin synthetics in this. The reason for this is because muscle cells need a collagen coating to allow them to communicate and differentiate properly to elongate. Without this, their cells just kind of stay in one place and do not properly grow. For the cell mixing process, we take the cells that have been growing in a petri dish, take those out, mix them in with our material, and then print and then cure using UV light and then incubate. Or we could plate the cells on top of the surface of our scaffolds after the scaffold's been sterilized and then incubate and grow. Cells are very adhesive, so this plating method works, and then obviously the cell mixing process is more traditional.
The main function of our project is to be able to contract cardiomyocytes to control a flow rate. The heart is connected to the nervous system, and since we are fabricating our own heart, there is no possibility we could connect a mechanical heart to a nervous system. This is why we don't have to think about our heart beating. Our body does it for us. We need to replicate this bodily function. To account for this, we are working to develop an electrical stimulus system that will deliver a shock to the muscle cells, as a result, produce contractions. We went about this by designing a circuit that will replicate how the nervous system sends stimulus to the heart. To prove that our circuit worked, we ran a test on an arm and checked if it would cause a contraction, and we were very successful.
For our printers, we switched to the BioX printer. Right now, it is using pressure to extrude the material as an additive printer, and from there, each layer is cured by a UV light, and then it does a final UV light curing.
Next, we had the Luminex printer, which is a DLP printer. It takes a liquid and using UV light cures the liquid onto a build plate layer by layer. The build plate rises to get our mold and model. Now looking at the Celsius simulation, we want to replicate a Celsius contraction. This is the same type of contraction that's in your throat that pushes food down. Using ANSYS, we know that the flow rate increases as the diameter decreases. And so we simulated a 1 millimeter flow through the inlet, and through the contraction, the flow would increase along the directions of the contractions one by one, and we got an outlet velocity of 4.6 millimeters per second.
For electrical stimulus, we used an Arduino, a relay system, electrodes, alligator clips, and wiring to cause a contraction in the forearm. We used the Arduino to program the relay as a switch, allowing us to change when we want to supply voltage. We were able to control when electrical stimulus was supplied. Additionally, we were able to control the amount of voltage and current using the variable power supply. This proved that the same can be done for cells using additional supplies, applying and wiring, and placing electrodes in the dish containing cells. In the future, we plan to run tests on stimulating cells.
In the cell culture, the cardiomyocytes were examined visually using a digital inverted microscope along with colored lenses, and they were all found to be healthy and viable. After the cells were counted in the petri dish, it was determined that the number of cardiac cells quadrupled over the first 5 days of cell culture.
It is a major endeavor with the potential to save millions of lives and have a huge influence all across the world. We have conducted an extensive study on the project's subtopics, such as cell culture, bioprinting, biocompatibility, tissue stimulation, and so on. As a result, as we move into the production stage of our schedule, we've outlined the protocols and procedures we will follow. The protocols and techniques for tissue culture are linked to the cells and culture material used. We've also looked into and tested a variety of bioinks for use in the bioprinting process. We have had many failed prints, but from each one we have learned important characteristics and variables from managing print quality. As a result, we decided to use a GELMA-based bioink as a framework for the muscular tissue and fibrin as connective tissue between the different layers. For the electrical simulation, there have been multiple additions to better suit the project's needs, and the changes were necessary to deliver electrical simulation with controlled voltage and current. These decisions have been one of the most difficult challenges thus far. There are numerous approaches that could present a solution to our proposed problem, but we are confident that we have chosen the appropriate materials and procedures to ensure the system's operation, taking into account the facilities, resources, and budget constraints. In the following phase of the project, we will merge the separate fields, electrical, bioprinting, and cell culture, to begin the manufacturing process and build our initial proof of concept and later prototype. We would like to give thanks to the Hardiman Scholars Program for providing us the funds to start our project. Also, to Dr. Behrooz Ovasi for the initial concept for the project. We would also like to give a special thanks to the Biology Department of Fairfield University for helping us with the cell culture process. More specifically, Dr. Shelley Phelan, Elizabeth Ricci, Kenesha Norford, Cassandra Riley, and Kate Junkins for introducing us to Dr. Phelan. Thank you for watching our presentation about our project. If you have any questions, feel free to contact us on the email shown.